A vector valued function is basically our combination of parametric functions and vectors. Okay? We basically take the idea of a parametric equation, but we are drawing the curve with vectors.
This was what my dad was talking about.
Yeah?
Yeah, my dad's a big math guy. He was in, I can't remember everything, but he used to be a chemist. He also got a degree in nuclear engineering. And, yeah, this was what he was talking about.
None of the ordered pairs for vectors.
Right, so instead of instead of two separate equations, we have it written together as one function where the instead of like our function for x, it's our component, our horizontal component for our vector, and our function for y is our horizontal component. Okay, so if I plug in 1, I get a vector which gives me the position on our curve. If I plug in 2, I get a vector, it gives me the position on our curve.
What is the real-life application?
Well, basically, we get to work with motion in two, like back in Calculus 1, we only worked with motion that was left, right, or up, down. Now we're going to be able to work with motion all over the place. So we're going to talk about velocity and acceleration on Wednesday with this stuff. Okay. So some things we talk about today are sort of things that we've talked about, but we have to like apply them to like our new way of writing these functions. Okay. So let's first talk about how we would graph a vector value function. Okay. So first of all, if this was my set of parametric functions, the vector value function would be this. Is there a glare from the sun?
There's no lights now.
Now some of us can already see what graph this would actually be, but let's go ahead and use our vector value function to figure out what the graph is. Okay, so what happens when we plug in 0? What is our vector? Okay, so we have the vector I, essentially. Okay. So we have the vector I, which means we have a coordinate right there. Okay? If we plug in pi over 2, what's our vector? Thank you. There's the vector j, which means that's our coordinate for our function. Okay, what about p of pi? Sounds very awkward. P of pi. And then p of 3 pi over 2 would be negative j. Okay, so our function, our vector valued function, looks like this. We're still gonna graph it the same way we do a parametric equations, but it is being drawn with vectors. Let's talk about the domain of a vector valued function. Sine of ti plus t to the 1/2 j is our function. What is the domain for sine of t?
Can you take the I, whenever it's with I? Whatever's within I.
Well,
so you have sine t with I, so it's
I want to look at these two separately. So what's the domain of sine of t? Okay. What is the domain for t to the 1/2?
0 to infinity.
So when we talk about the domain for r of t, we have to look at where those overlap. Yes, I can plug negative numbers into sine of t, but I can't plug negative numbers into t to the 1/2. So wherever these two overlap, that is where our domain for our vector value function.
what about the range?
The range we would have to identify after we graph. All right, so how do we take a vector valued function and figure out what the graph actually looks like without having to plug random values in? What are we going to do? I told you this was a mesh between parametric and vectors, right?
We set x equal to 2 cosine t and y equal to sine t, and
Yes.
then mesh them together.
Okay. This vector value function is representing a set of parametric equations where x equals cosine t and y equals sine t. So what we can do is we can eliminate the parameter to get our graph. Okay. You could probably get this graph by plugging in random numbers, but not always is that going to be the most efficient way to get our graph. Okay. And this is a good reminder for us. How do we eliminate the parameter when we are dealing with sine and cosine? Okay. Can you be more specific?
Like a sine squared, whatever. Sine squared plus sine squared. It's weird with the squared.
Cosine squared plus sine squared equals 1. Cosine of t is the same as what? Careful. X over 2. And sine of t is the same as y. So what we have is x squared over 4 plus y squared equals 1. Do you remember what that is? We talked about this last week. What did you say? Yes. An ellipse at 0, 0, where we're going to go 2 out horizontally and 1 vertically. which direction does this go? Does it go clockwise or counterclockwise? And how do you know that, Zach?
Because of the loading values.
Okay. If we plug in 0, we're at this coordinate. If we plug in pi over 2, we're at this coordinate. So we're going counterclockwise. Do not forget to put in those directions for both parametric or these vector value functions. I will take out points if I don't have those. All right. So we're going to talk about a few things with vector value functions that maybe you think are obvious, but we still need to talk about them. Like the limit of a vector value function. Okay? If we have a vector value function and we're looking at the limit as t approaches some number, then we can look at the limit of each piece separately. And we're still going to end up with a vector after we take the limit.
Should RT and PAT or RT and PAT basically the same thing?
We can name our function whatever. The most common you're going to see will be R of t and P of t. But you know kind of how we have f of x, g of x, h of x. We can name our functions different ways. Is that what you're confused about?
We'll check. I'll come back to it later.
Okay. So, for example, if I asked for the limit as t approaches 0 of e to the ti plus sine of t over t, okay, we're going to take the limit of these two functions separately. So, Sammy, what is the limit as t approaches 0 of e to the t? E to the t when we plug in 0 again. Okay, so since this limit is 1, we have 1i plus the limit as t approaches 0 of sine of t over t.
Which is 0 over 0.
Okay. So we would have to use the L'Hopital's rule, right?
This is just 1.
That's also one of those rules you learned in like the first week of calculus. So our limit is the vector I plus j.
It's minus 2 to square root of 2.
What?
That's minus 2 to square root of 2.
Yes. But we don't. Okay. Also something we have to talk about, since we're talking about limits, what goes really nicely with limits? Starts with a C. No. Good try. Continuity. Okay, so let's talk about the continuity of a vector value function. you to do is you and the person you sit next to talk about the definition of continuity for just a regular function. There are three pieces to the definition of continuity. See if you can come up with it. 1, 2, 3, go.
You don't need it stable difference, right?
What is that one difference? It's not just a limit, it's also the point, right?
Yeah, the limit, the point, and then everything.
Yeah.
The limit has to. And then it has to be differentiable.
I don't think it has to be different. Yeah, it could be a sharp corner.
You learned about continuity before you knew what differentiable meant.
It's the limit has to be the same, the point.
I thought we were talking to the people next to us.
I'm sorry.
Okay.
Hey. You already reached part of the last one. Where you go?
Limits, yeah.
But I'll figure it out.
Okay, so Gabby and Josh, give me one thing.
The limit must exist.
Okay? One more thing?
Yeah.
Yes. And
Limits from the left and right are equal.
that is the limit existing.
Okay.
The limit exists. The point exists.
They're the same.
And they have to be the same. Okay. So, same thing here. If R is continuous at T equals A, then that means that, number 1, the limit as T approaches A of R of T exists. R of A exists. And R of A equals the limit as T approaches A of R of T. Okay, same 3 conditions, except now we're dealing with a vector value. Okay, I would like you and your neighbor to talk about where this function is continuous. Where is this function continuous? You may have to speak to each other to do that.
Wait, and 1 is not inclusive. Okay. At least when it comes to continuity. No, it wouldn't be inclusive.
Yeah, it's including one.
But
It is including one.
you would typically have to include 1 because it's still.
You can take this off there.
You're saying this?
This is exactly what we're saying.
Because the limit may not exist from the left, but it's still technically there. Like you can't just ignore it. It's not.
Okay, so what's happening here is we would have like endpoint continuity. Does that make sense? Since the domain starts at 1 and goes to infinity, then we would be continuous at 1 because that's where our function is starting. Okay? Excellent. Now for the fun stuff. What comes after continuity? Derivatives. Okay, so this should look familiar to you, right? The derivative is the limit of the difference quotient. Okay, so we are going to do a general limit of the difference quotient to come up with how do we really take the derivative. Okay. We will be using R of t is f of t I plus g of t j. Okay, so we have the limit as h approaches 0. R of t plus h means we're plugging t plus h into our function minus R of t all over h.
Would it be a touch easier to put it in the, whatever you call these?
No. Well, we're going to write them with i's and j's. Okay? That's essentially what we're going to get at here. Now, can we rearrange this? I am going to separate this into two fractions while rearranging. Can we do that? Two things at once? Are you okay with that? Basically, I'm going to add two fractions. We still have the denominator of h. I'm just going to split this apart. So I'm going to group f of t plus h I together with minus f of t I. And then I'm going to group g of t plus h j together with minus g of t j. Can you maybe see where this is going? We essentially have the limit as h approaches 0 of f of t plus h minus f of t all over h I plus the limit as h approaches 0 of g of t plus h minus g of t all over h j. Now I have two limits. I factored out the i's and j's. What I just underlined in red, what does that mean?
Derivative of f.
And what does that mean? Okay, so good to know. All we have to do is take the derivatives of each component. Done. We can do that, right?
So that was just a proof?
Yeah.
Okay.
We like to know where things come from, right?
Yes.
Okay. Okay. Now remember, this is the derivative with respect to t. Much different than if I were to ask for like du dx, right? Okay.
And
So
just be buying Dan low.
what?
And we're taking the derivative, you would just leave I and J alone, as if they don't exist.
Well, they do exist. You just keep them.
Yeah, that's the thing.
It
You can
remains
ignore
a
them.
vector.
You can ignore them until the end product.
If you want to look at it that way. Okay. Okay. Now, Zach, were you saying like you would like to write it as this?
That's what I was saying.
Okay, I can't remember who said it. Okay, you will probably see both ways. Okay. Okay.
Yeah, that's what.
You will see both forms, so just be prepared for that, be able to recognize. The book uses a lot of the IJ form. The AP test uses more of the component vector form. So let's talk about R prime. Everybody, what is the derivative of T?
-1.
Let's try that again. What is the derivative of T? What is the derivative of 4 minus T squared? Okay. Monday we have some cobwebs to, All right. Let's talk about this graph right here. Okay. What do you think that graph looks like? Any guesses?
No.
Okay.
Oh. Is it just linear?
It is not. What is the vector we get when we plug in -2?
-0.
Okay. What is the vector we get when we plug in -1? Negative I plus 2j, right?
So when you plug in 0, you get 0, 4.
Okay. What about 1?
Parabola.
1 plus 3.
Oh. No. There. Okay. If I asked you for R prime of 1, that would be the vector I minus 2j, correct? All right. Since this is the derivative at 1, what kind of vector is that? There we go. So if I were to take this coordinate and draw the vector, let's see, I minus 2j, it is tangent to our curve. What if you are asked to give a normal vector at t equals 1? What would a normal vector to t equals 1? This is the tangent vector. What would the normal vector be? Let's think about this. What is the slope? Like if we look at that vector, when we drew it, right, we went to the right one and then we went down 2 to draw it. So we kind of visualize that having a slope of -2, correct? So the normal vector would have to have a slope of what? Positive 1/2. So a normal vector could be the vector 2, 1, because that would have a slope of positive 1/2. Or it could be the vector -2, -1, because that would have a positive slope. And that would be the normal vector.
Oh, so you
Yeah, I don't understand that either.
Because
The tangent vector?
I don't
No,
know
no,
graphing the
derivative.
derivative. Graphing the derivative at all.
Okay,
I'm confused on this graph here.
Yeah.
that black graph
Yeah.
is this, the original.
Okay. I thought you were graphing the derivative.
Okay, that would make less sense. I'm sorry that was not clear. So we were graphing the original, so we just plugged in t values to get the parabola, so that here the derivative we could graph these tangent vectors. Okay, we're all on the same page now.
well, the normal vector is just a unit vector, right?
No, normal vector is not even. Normal just means perpendicular to the tangent, perpendicular to the curve,
Oh.
essentially. All right, let's go ahead and revisit the concept of a curve being smooth. Okay, when we were talking about parametric equations, Sean, what did it mean if our curve was smooth?
It was differential at all points.
Can you go into a little bit more detail on that one?
It was differential at all points.
Well,
You mean for parametrics,
uh-huh,
no vertical tangents? I don't really remember.
okay. It's okay to have vertical tangents, and it's okay to have horizontal tangents.
But
Oh.
not the same time.
Okay, but it's not okay to have them at the same time, okay? So if we have, if we're talking about our curve being smooth, our derivative can't be the 0 vector, okay? If our derivative is the 0 vector, meaning both components have derivatives of 0, then we are not smooth. Okay, so let's talk about r prime here. Okay, Bailey, what is the derivative of t plus sine t?
Cos t. 1 plus cos t.
All right. And Sammy, the derivative of 1 minus cosine t. Okay, so this curve is not smooth if 1 plus cosine of t and sine of t are 0 at the same time. So let's figure that out. When is sine of t equal to 0?
0, pi, and pi n.
Right? Okay. When is 1 plus cosine of t equal to 0? Essentially, when is the cosine of t equal to -1? Pi, and then 1 would be the next place. 3 pi, and that would continue, right? Okay, so do we have some overlap?
Yes.
Yes, which means we are not smooth when t equals pi, 3 pi, 5 pi, etc., which we could label as pi plus 2 pi n. Pi and then in increments of 2 pi, right? Okay. It's okay for f prime of t to be 0. It's okay for g prime of t to be 0, but it's not okay for them to be 0 at the same time. All right. Last concept. What comes after taking derivatives?
Intervals.
Technically, yes, second derivatives.
Intervals.
Didn't see that coming. Going for integrals. Okay?
Wait, can you go back to what's in my book?
To what?
Oh, there you go. I just didn't know exactly how to react that.
Okay, so basically, we can take an antiderivative. We would just need to do it with each component separately.
Wait, DG out. I was just a little confused about the DTI.
Oh, that's like the vector, right?
That's-
If that helps.
Yeah.
Okay, so if I'm asking you to take the antiderivative of a vector value function, okay, then essentially what I would like you to do is take the antiderivative separately. Okay.
Do we use the plus C?
Well, yes, but we haven't taken the antiderivative yet.
Okay.
So the antiderivative of e to the t is e to the t plus c. I'm going to put it as like c1. Okay, so you can separate the two. Antiderivative of sine of t is negative cosine plus c. So essentially what we have is e to the t I minus cosine of t j, and then notice how I have a constant times I plus a constant times j, so we can write we are going to be adding a constant vector. So we still have that plus c, it's just plus c as a vector. Does that make sense? Okay, so we've covered a lot of calculus topics, but they're all something that you've seen before, right? It's just we're working with vector value functions. You have a very short homework assignment. You can find it on your gold sheet. It's a book assignment. It's actually your only book assignment, your last book assignment for the rest of the year, for crying out loud. So tomorrow we will finish our discussion on vector value functions. We'll talk about like the fundamental theorem of calculus, or taking like initial conditions and finding vector value functions. Then you'll have the worksheet tomorrow. Wednesday we'll talk about velocity and acceleration. Okay? Welcome back to school!
Yay!
Haley's back.
Yay!